Hi, my name is Stian Midlom, and I'm here to present the paper ERTEC 2765 titled Black Oil in Compositional Reservoir Simulation of Gas-Based EOR in Tight Unconventionals. This presentation will start by looking at the purpose of the study and then walk its way through the main aspects of the paper, that is the fluid model, reservoir model, and simulation results, before we provide a small discussion on how to improve a black oil PVT model, and then arriving at the conclusions. So the purpose of the study is, by using a lumped Eagleford field-wide EOS, to 1. Simulate 2 EOR processes compositionally, and 2. Create black oil PVT tables, and also by using a simple reservoir model, and by using a set of comparable metrics for simulation with black oil PVT and compositional models, we attempt to answer the following. Can a black oil PVT model be used to accurately simulate the performance of the following EOR processes: the well-known Huff-n-Puff process, and a less-known alternative, the fracture-to-fracture process? And if not, is it possible to alter the black oil PVT model to improve recovery predictions? So we put a lot of emphasis in the paper on the fluid model, and there are 2 fluid models in reservoir simulation, the one being the black oil PVT model. The black oil PVT model has 2 formulations. The one is the traditional formulation, which you find in most textbooks, which tells you that oil at reservoir conditions processed at the surface gives you 2 products, a surface gas and a surface oil. And if you have a reservoir gas and you process it at the surface, you get only 1 product, a surface gas. The modified formulation, which we have used, throws in a second product when you process a surface gas, and that is process a reservoir gas, and that is a surface oil. Now, a black oil PVT model is based on black oil PVT tables, which is table values of the volumetric properties that you need at a given pressure. And of course, the entire black oil table is generated at some temperature, normally the reservoir temperature. The black oil PVT table consists of 2 sets of properties. You have the saturated properties that were shown here, which we again divide into 2 parts. The lower part, which you get from performing some depletion experiment on the initial reservoir fluid, and the upper part, which you obtain from an extrapolation method. And this is something we discuss in detail in the paper. Now, once the saturated properties are obtained, we estimate the undersaturated properties. That's the second set of properties in a black oil PVT table. At any saturation pressure, at a higher pressure, taking that fluid to a higher pressure, i.e. maintaining it a single phase, these undersaturated properties gives you the volumetric behavior of that phase. The second fluid model in reservoir simulation, and the second fluid model that we're using, is the compositional model, which is based on an equation of state that in practical sense consists of 2 tables, the component properties shown here, and the binary interaction parameters, which is a symmetric matrix. And the equation of state works by feeding it a composition, pressure, and temperature, and it returns the volume of that mixture at these conditions. The reservoir model in the paper is chosen to be fairly simple, to put emphasis on the comparison, which is not on reservoir models, but on the fluid model. We use a well box shown here, which is symmetric, such that we only simulate a part of this well box and scale up with the corresponding number of fractures. This model we call a symmetry element model, And it consists of, as you can see here, a hydraulic fracture on each side, shown with the black thick line, a blue region on each side, which is the shattered volume, we'll get back to what that is, and in the middle is a gray area, which is the matrix. Now, the two EOR processes are modeled as follows. The Huff-n-Puff has both injection and production from both fractures, whereas the fracture-to-fracture is, as the name suggests, you inject into one fracture and you produce from the other, leading to a displacement type process. The gridding of the reservoir model, the symmetry element model, is as follows. The shattered volume is treated with a dual porosity formulation, meaning that we have flow from grid block to grid block in the fracture layer, and the fracture layer can drain or inject into the matrix block connected to it. The matrix region is modeled with a fine grid single porosity formulation, or just regular gridding, and of course the model is symmetric, so each side is both sides are equal. The well perforates the fracture layer and in this case represents the hydraulic fracture. We have another model we also look at, which is the single cell model, and the single cell model just consists of one pair of dual porosity grid blocks. That is one fracture block and one matrix block with a well connected to the fracture. This single cell model, we use this to study the details of recovery, particularly for the Huff-n-Puff process, as we believe that the dual porosity region, or this shattered volume, is really the target volume for the Huff-n-Puff process. And we believe that modeling the Huff-n-Puff process on one of these pairs of grid blocks will give you an expected upper recovery profile, and I'll get back to later on what I mean by upper performance of the Huff-n-Puff process. And to look and to study and compare the details, we look at the oil saturation and gas saturation in the matrix cells, the producing oil-gas ratio, and the produced oil in terms of an oil recovery factor. So the simulation results are as follows. Before deep diving into the results, I just want to show high level the workflow of the paper. So for all cases that we present, we have initially an initial conditions, an EOS, or a set of initial conditions, an EOS, and a reservoir model. And for the compositional case, we simply feed those three to the reservoir simulator and we run the simulation. For the black oil PVT simulations, we take the equation of state and initial conditions, we feed it to the PVT simulator, which gives us the black oil PVT table, and we bring that table along with the static reservoir model to the reservoir simulator and we run the simulations. Now, once both simulations are finished, we take the results, we post-process them, and we compare the results. So we look at many cases in the paper, and I'm just going to show one here for the single cell model, which is shown, as I mentioned, in 4 different plots. Now on the top left here we have the oil saturation in the matrix cell, which shows you the first 2 years of depletion and then the consequent Huff-n-Puff cycles. We see initially that the saturations are predicted fairly well for both fluid models. The solid line is the compositional and the dashed line is the black oil PVT model. But once the fluid transitions from being a single phase oil to being a single phase gas, the difference between the fluid models becomes bigger, and we see that the black oil model just removes more and more oil each cycle, whereas the compositional model has a much longer duration of oil in the matrix. and actually at some point after a few cycles is not able to maintain single phase even at the highest pressures. We see here it's actually two phases at the entire pressure range. Of course, the right plot here is the gas saturation. That's just 1 minus the oil saturation and connate water saturation, which in this case is the 20% on top here. The producing OGR, the producing oil gas ratio, we'll get back to that plot. But really the key plot that tells everything is this oil recovery factor, where we see that from the second cycle and onwards, there is a difference, a non-negligible difference between the two fluid models, and it increases with the number of cycles. So the key takeaway from the single cell modeling is that all 5 fluid systems that we simulate in this in the paper given in this table here show that the black oil PVT model overpredicts oil recovery. We also show that the difference between the black oil PVT and compositional models increase with increasing initial solution gas oil ratio, meaning that at least this gap here at the final recovery factor becomes bigger as the fluid becomes a more volatile oil and transitions to a gas phase initially. Now the natural question to ask then is, why is oil recovery predicted or over-predicted? And to understand this, we need to look at high level at the 2 parts that controls the recovery. And the one part is this part here, which for the sake of the argument, we look at the 3rd cycle, and the part we're showing here is the part you recover when the bottomal flowing pressure is higher than the saturation pressure. And what this plot shows you is the gray line shows you the pore pressure in the matrix grid block. The pink line shows you the predicted saturation pressure from the compositional model, and the blue line shows you the saturation pressure for the black oil model. The prediction of the saturation pressure is important because it controls when you start to produce 2 phases instead of 1. Now, the nature of a gas-based EOR process is large gas volumes, resulting in most of the cycles here behaving as when you produce back, i.e. the puff period, the fluid behaves as a gas condensate system, where the gas condensate becomes leaner with each cycle. And we know that a gas condensate producing from a gas condensate reservoir is most efficient in terms of condensate recovery when the gas reservoir is single phase. That's when you recover a constant amount of oil for a certain rate of gas. When you drop below the saturation pressure, oil starts coming out of solution, but none of that oil is recovered. What drops out in the reservoir stays in the reservoir. That's a general rule for gas condensate reservoirs. And of course, the condensate recovery efficiency drops as a result of that. So predicting the saturation pressure correctly will have a major impact on how much oil you're able to recover each cycle. The other part that is important to look at is when the fluid system becomes 2 phases, which in this case is reflected by the saturation pressure being equal to the cell pressure. What happens then? What controls oil recovery then? And that's really the gas's capacity to carry oil in solution at some pressure. The red line here shows you the little RS of P curve, or the inverse of that, for the black oil model, the thick red line. And that's the line that you move up and down with pressure in each Huff-n-Puff cycle when the cell is 2 phases. Now, if you take the compositional model and you extract the daily compositions from the matrix cell, you process those compositions, and you calculate the inverse solution OGR, you get these thin lines. And we definitely see that these are not constant. They are increasing with time, meaning the little RS of P is decreasing with Huff-n-Puff cycle. Now, what does that mean? It means that the gas's ability to maintain oil in solution drops with Huff-n-Puff cycles. So you should expect to recover less and less oil in the two-phase period with Huff-n-Puff cycles. So going back to the 4 plots and looking at the details of the producing OGR, we can see what happens. What we just looked at is shown just from this. We can look at this here, which shows that the plateau, the black oil model, again is the dashed line. We see that the black oil PVT model predicts a far too long a plateau production, indicating constant composition removal, and the final little rs at the minimum flowing volatile pressure is twice as high as what the compositional model is. And we know that the oil recovery is for a gas system is often expressed as a producing OGR times the gas rate, and integrated between the from end of Huff, that's essentially here to through the entire puff period. And we know that if you produce at a constant gas rate, this profile here is essentially just the oil rate profile, or the condensate profile, if you will. And the difference predicted from the black oil PVT and compositional models is directly proportional to the difference in the RP curve. And this RP curve here reflects the difference in the predicted little RS curve for the two models. So the underpredicted saturation pressure gives you too long a period of single phase removal, and the fact that the black oil PVT model overpredicts the oil solubility in the gas phase gives you this too high and this too high of a producing profile when you drop below the saturation pressure or the dew point pressure. So looking at the results, some of the results for the symmetry element model, we're just going to show the simplest cases here. We have 3 oils and 2 gases, and we can see that in all cases the black oil PVT model overpredicts recovery as expected. Now, what can we take away from this? The difference in recovery, the final difference in recovery, is not just a function of the initial solution GOR, it's also a function of how big the shattered volume is, how large the extent of the shattered volume is. Had we made the entire reservoir model dual porosity region, this profile would look much like the single cell model, and that's why I called the single cell model an upper limit of recovery for the Huff-n-Puff process. Of course, the lower limit would be if you had no shattered volume, which would give you just a flat line here with no incremental recovery, and there the models should overlap. And one thing to take away from this symmetry element model for the Huff-n-Puff is that the black oil PVT model overestimated the recovery for all the cases, not just the ones that were shown here. So say you have the problem that you don't have an equation of state, or you want to use the black oil PVT model for many reasons, one of them being that compositional models run much slower than a black oil model. Is there any way to improve or alter the black oil PVT model such that it actually can predict these recovery processes, at least with a higher degree of accuracy than what we have seen so far? We're going to look at the volatile oil system, where we have tried to alter especially the little RSFP curve with number of cycles. Now, there are different methods of doing this. What we have done is just to recurrently change the black oil PVT model that governs the shattered volume with cycles. So we have taken, at every cycle, we have given a new set of black oil tables in that region to the reservoir model. And the result of that can be shown for the pink line and the gray line, where the two lines are where the compositions we've used to generate the black oil tables are found in 2 different ways. The method 1 is a fairly simple one, and it mimics quite closely what you would get if you used, for example, the GI option in Eclipse 100. And the method 2 is, of course, you see it's almost on top of the compositional one, but to obtain that degree of accuracy, you actually have to do a compositional run because you need the solid compositions extracted from the compositional simulation. So you're sort of back to square one then. So the conclusions are as follows. A compositional fluid model is always preferred when modeling gas-based EOR. That's what we've found both for the Huff-n-Puff process and for the fracture-to-fracture process. The black oil PVT model has in all cases overpredicted oil recovery for the Huff-n-Puff process, and it does so because it underestimates saturation pressure over time and it overestimates the solution OGR with time. The black oil PVT model actually gave reasonable results for the fracture-to-fracture process for low to medium GOR oils. We didn't show that in the presentation, but it's in the paper. And recurrently changing the black oil PVT tables or using some other method of correcting the RSFP over time can actually improve the results of using black oil PVT model for simulating the Huff-n-Puff process. That is the modified black oil PVT model. And with that, I thank you all for your attention and look forward to answer any of your questions.